Hello grade 10s and welcome back to my channel. I'm Miss Martins. If you're not subscribed, please subscribe now. I do maths, I do physics, I do chemistry. In this video, we're going to be looking at electrostatics. And this is like a summary of grade 10 electrostatics. I hope this helps you. I will do more videos where I go into each little bit of the topic in more depth and where I practice a lot more practice questions. So keep an eye out on this playlist for more videos like this. Let's jump right in. Jump right into the summary and start off strong with definitions. As you should know, definitions are a massive part of physical sciences. If you don't state the definition correctly, you don't get your marks. And definitions are supposed to be like level 1 or easy questions. So grade 10s, this is the definitions for this grade. The principle of conservation of charge and the principle of charge quantization. Those are the only two definitions that you need to know in grade 10. In grade 11 and in grade 12, you don't even need to know these definitions. You need to know these definitions, completely separate. Obviously, if you're in grade 10, this only comes in grade 11 and in grade 12. Grade 11s and grade 12s, you learn these definitions, but grade 10s, these are the definitions for you. However, it is good to go over these definitions and make sure you understand what it means, whether you're in grade 10, 11, or grade 12, because they relate to these two formulas, this one over here and this one over here. And these two formulas, although you learn it in grade 10, they can ask it to you and you have to apply it in grade 11 and grade 12 as well. So remember, definitions, you just have to learn it. So you may have to pause the screen, take this down in your book, memorize it, and then that's it. All right, now, for the formulas, as you know, you cannot do physics, you cannot do chemistry without your formulas. And in grade 10, these are the two formulas that you need to know. Just those two. These are given to you on your data sheet, on your formula sheet. Instead of this one, you might see a version that looks like this for grade 10s. They are the same thing. You're either going to get E at the bottom or QE at the bottom. They mean the same thing. They're the charge on an electron. They are the charge of one electron. I'll go through what everything else means in a moment, but be familiar with these definitions, grade 10s, 11s, and 12s. You are taught it in grade 10. Obviously, in grade 10, it's the only definitions you need to know, but in grade 11 and grade 12, you still need to know these. You still need to be able to apply it. In grade 11 and in grade 12, this is what your formula sheet looks like. And I hope you notice that in grade 11 and in grade 12, they don't put this formula on the formula sheet. However, you still need to be able to apply that formula if need be. So if the situation arises where two objects come into contact and electrons are transferred, you need to be able to apply this formula. So again, it's something that you learn in grade 10, but it carries through to grade 11 and in grade 12. So let's focus, because this is about a summary of grade 10 electrostatics. We're going to focus on these formulae. So what I want you to do is, when you summarize electrostatics, I want you to make a summary of the formulae to be used in this section. This formula over here on the right is used when two objects come into contact, they touch, and then they're separated again, and the question asks you to calculate the final charge of one or both of the objects after they touch and separate. For this formula, and maybe we should actually start off with the fact that in electrostatics, Q is charge. So Q is the symbol for charge. So instead of writing out the full word charge, we can use the symbol Q. And the unit for charge is something called coulomb. Coulombs or C. So for example, if I say Q is equal to 3C, what I'm saying is the charge of an object is 3 coulombs. You can get charge being negative, or you can get charge being positive. You can also get charge being 0. You get charge, the unit in coulombs. We also get the units as being something like millicoulombs, microcoulombs, nanocoulombs, and picocoulombs, which I will chat about later, but you have to convert these to coulombs for some formulas. Right, so charge is Q. That's the symbol. That's the symbol. The unit is coulombs. So Q1 is the initial charge of object 1. Q2 is the initial charge of object 2. And Q is the final charge. And what's important about Q is it is the final charge of both objects. So that is very important. And obviously the unit for all the Qs is coulombs, or C. We're dividing by 2 because there's 2 objects coming into contact. And I will go over this formula in more depth in a little bit, but it's important to substitute the signs into this formula. I will explain what I mean later. So this formula is basically the principle of conservation of charge. That is when we apply the formula. So basically says charge remains constant. Then our second formula is N is equal to Q over QE. Remember I mentioned that instead of QE, they can just say E. N is number of electrons. So we use this formula whenever we are asked to calculate the number of electrons. So that's what I said here. This formula is used when looking for number of electrons or amount of electrons. We can use it to calculate the number of electrons added or removed in order to give object charge, or we can use it to calculate how many electrons were transferred or how many electrons moved during contact. So N is number of electrons. Q, this is change in charge. And I will make mention of this when we go over this formula in more detail, but this Q is not the same as this Q. They are different. In this formula, this Q is final charge. In this formula, this Q is change in charge. And I want you to think of that as final minus initial. I will get into that in more detail. And as we've mentioned, this is the charge on an electron. And what's nice about that is the charge of an electron will always be the same. It's always negative 1.6 times 10 to the negative 19. Always, 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 always. It will never, never change. Right. As I said, we will get into both of these formulas in a little bit more detail in a second, but for now, I want to just focus on a very brief overview of the theory of electrostatics. Electrostatics is all about charge. It's all about electrons. And the first thing that you need to know is that materials, so objects, surfaces, me, you, everything around us is made up of atoms. And atoms contain positive protons, so protons are there, they're found in the nucleus, they're positive, and negative electrons. And as you should know, electrons are found in the outer orbitals. So we also have neutral neutrons, but those aren't really involved here. What you need to know, and this should make sense, protons are positive, electrons are negative. If the number of protons equal the number of electrons, the atom is neutral and the material is uncharged. So the charge is 0 coulombs. Like in this case, 1, 2, 3 protons, 1, 2, 3 electrons, 0 coulombs, neutral charge. And that's what this says over here. If you are neutrally charged or uncharged, it means you have an equal number of protons and electrons. The net charge is 0. They often ask you to describe what it means to be neutrally charged or uncharged, and that is what you will say. Positively charged, they have more protons than electrons. And what's important to state is actually that they have a deficit of electrons. So deficit means a lack of electrons. They have lost electrons. They have less electrons than protons. And that's what makes them positively charged. Now remember, electrons are negative. So if you lose electrons, you're losing the negative stuff, leaving you positive. Negatively charged objects have more electrons than protons. They have an excess of electrons, which means they have a lot more electrons than protons, and therefore are negative. And there's a summary of that. It is super, super, super important to note that only electrons can move. Only electrons. So an object can gain electrons, an object can lose electrons. Protons cannot move. An object acquires a negative charge, so it becomes negatively charged by gaining electrons. Remember, if you get negative stuff, you become negative. An object acquires a positive charge by donating or losing electrons. If you lose all the negative stuff, you will become positive. And again, only electrons can move. And how does this work? Electrons can be rubbed off. So electrons can rub off from one material to the next. So in this case, we have a rod. It is rubbing against a cloth. From the arrows in the picture, we can see that the rod is losing electrons. So electrons are being transferred from the rod to the cloth.
that means that the rod will have more protons. It'll have more protons and electrons. It'll have a deficit of electrons because the electrons have left, which means that it'll have a positive charge. The cloth gains electrons, therefore it'll have an excess of electrons and it'll become negatively charged. Okay, so that is how it works. The electrons and protons will no longer be balanced. Okay, here's another example. Now remember I told you that charge is measured in coulombs. Remember we said coulombs is C. So for example, you can be 3 coulombs or -2 coulombs. But they might give you the measurement for charge in different units, such as picocoulombs. These are tiny little units of measurement. It's kind of like instead of saying meters, we have millimeters. And you know, millimeters are much smaller than meters. It's the same thing. So millicoulombs, microcoulombs, nanocoulombs, picocoulombs. This is how they'll show it to you. So for example, they'll say that the object has 3 nanocoulombs. Then you need to know, okay, cool. 3, to convert it to coulombs, I must times it by 10 to the power of -9. So what you do to convert it to coulombs is you just times it by whatever this says over here. So another way that I remember it is nano is 9. Okay, pico is 12, micro is 6, and milli is 3. Well, -3, -6, and so on. The charge of an electron is this. That's a constant. And remember, with our formulas, we call it QE or we call it E. A proton has the same charge but opposite. So instead of a negative, it has a positive. Now, remember the first definition in grade 10 that was important is the principle of conservation of charge. And what that means, so obviously you study this if you're in grade 10, you learn this off by heart, the definition. But what it means is if I have 2 identical objects on insulating stands and they touch each other and then they separate, both of them will end up with the same final charge. And obviously this is only true if they are identically sized, right? And this is the formula that we use in order to calculate it. And we've been over the formula before. Just remember, if it's 2 objects coming into contact, we divide by 2. If it's 3 objects, it's divided by 3. And as I mentioned earlier, signs are very important to substitute into this equation. So if we have to do this as an example, we've got a positively charged sphere A, 3 nanocoulombs, and a negatively charged sphere B, which would therefore be -4 nanocoulombs. And they come into contact and they separate, and they want me to calculate the final charge on both spheres. Essentially, I need to use this formula because I've got 2 objects coming into contact and separating. So this is the formula that I use. Then you substitute in. Q1 is this. And I'm going to just change it from nanocoulombs to coulombs. Remember, you times by nano, 9, times by 10 to the -9. So we've got 3 times 10 to the -9 plus, now the second sphere is negatively charged, which means -4 times 10 to the -9. This is what I mean by you have to substitute the signs in. I say it over here. Substitute signs into this equation. So if one of them is negative, you must put the negative in. And we're going to divide it by 2 because there's 2 spheres that are coming into contact. And my answer is -5 times 10 to the power of -10 coulombs. Okay, it's very important. Now, a few things here. Please use brackets on your calculator when doing this. Type in the signs correctly. You might have to use the small little negative sign in your calculator, not the big one. If you look carefully at certain scientific calculators, you'll see that there are 2. Please type it in carefully. Make sure your calculator is on the correct mode. Reset your calculator if you must, back to normal. That is what you should get. Now, basically what this means is before they touched, that was A's charge, that was B's charge. Then they touched and electrons were transferred. When they separated again, they had the same final charge. So this is the final charge. A has that final charge and B has that final charge. And another thing that I want you to take note of is which way the electrons move when they are touching. So remember, the reason they both end up with the same final charge is because when they touch, electrons move. Now, which way do you think electrons will move? How electrons move should make sense. They move from the more negative object to the less negative object. So the one with more electrons to the one with less electrons. So electrons move. That's it. Electrons move from the object with more electrons, so the more negative object, to the object with less electrons, so the more positive object. It makes sense. If you have a lot of electrons, you want to give some away. You're like, oh, shame, this guy has less electrons than me, so I'm going to give it to them. Okay, that is how electrons move. And just remember, if I have 3 coulombs versus 5 coulombs, which way will electrons move? From the 3 coulombs to the 5 or the 5 to the 3? Well, neither of them are negative, but this one is more negative. It's closer to being negative. It's less positive, if that makes sense. So electrons will move from the more negative to the less negative. The next formula that you need to know has to do with the principle of charge quantization. Now, this sounds very fancy, it sounds very complicated, but basically it just says that every charge in the universe, so every object that has a charge, that charge is an integer multiple of the electron charge. So what that means is you take the charge of an electron and you times it by an integer. And you should know that integers are like 1, 2, 3, 4, 5, and so on. So if I times it by 2, if I times it by 3, if I times it by 4 or 5 or 6 or 1,000 or 1 million, that can potentially give me the charge of an object. You cannot multiply the charge of an electron by something that is not an integer, like 1.5, to get you the charge of an object. It doesn't work like that. It has to be an integer multiple. Okay, what that also means is if I know the charge of an object and I divide it by the number, the charge of an electron, then I can work out the number of electrons that object has extra or that object has in deficit. If that is confusing to you, don't stress. I will teach you what this formula means and how to use it. But what you do need to know is that this over here, or they can represent it by E, that is a constant, it's that value. And it'll always be that value. Technically negative, but what these lines mean is that we can ignore the negative. We can take the absolute value. We can ignore the negative. I'll explain what that means in a second. But remember, earlier on I said that N is number of electrons. This is the charge on an electron, which is that over there. And that is not final charge. Remember, this Q is not the same as this Q. No, this Q is final minus initial. Just keep that in mind. Right. When do we use this formula? I like to break it down into 2 situations for my students because it might help them. The first situation is when you are asked how many electrons were added or removed from an object to give it its charge. So for example, if I say my object's charge is 3 coulombs, and I ask you, how many electrons were removed to give it this charge? It doesn't just get that charge. Remember, that's a positive charge. I must remove electrons. I must take away negative stuff, electrons, to make it positive. And the question could say, how many electrons? How many electrons must I remove? If that's the case, we use this formula and just think about it. It makes sense. We're looking for how many electrons. We're looking for a number of electrons, which is N. The second scenario in which we use that formula is if we have 2 objects, they touch, electrons move. Remember, electrons move from the more negative object to the less negative object. And then they ask how many of those electrons actually moved when they were touching. So did 1 electron jump over? Did 2 move? Did 3 billion move? That's when we use this object. And then Q is the final charge minus the initial charge. So let's do this example first. Very similar to the one that I made up a few seconds ago. They could say how many electrons were removed to give a sphere a charge of 3 microcoulombs. Now, first of all, how do I know that electrons were removed? Because electrons are negative and this charge is positive. So when we remove the negative stuff, we leave it with a positive charge. Now, all you do is you take your formula, you write it down, you substitute. So in this case, Q is the charge of the object. That's the charge. But remember, we must convert to coulombs. How do you convert microcoulombs to coulombs? You have to memorize it. You times it by 10 to the power of negative 6. So it's 3 times 10 to the power of negative 6. And in the place of QE or E, we put the charge of an electron. Yes, electrons are negative, so you can put the negative there. But please, please, please remember that we are calculating a number of electrons, and you cannot get a negative number of electrons. And I've said this before in one of my videos, and I say it to my classes all the time, and I'll say it again in this video. If someone asks you, and you can think about this question yourself, how many chocolates did you eat today? You're either going to say nothing, I ate 0 chocolates, or you're going to say 1 chocolate, or 2, or 10, or 20, hopefully not. But you never say negative. You don't get a negative number of something. You don't say, ma'am, I ate negative 1 chocolates. That makes no sense. It's silly. It's the same thing with electrons. You can only have 0 electrons, or 1, or 2, or 3. You can't have a negative number. So if you put the negative in there, it's fine. Just remember to write your answer as positive. So always a positive answer. Always, 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 always a positive answer. If I type this into my calculator, a teacher tip is to use brackets, please. It makes a difference. My students and I have found this over the years. And I get 1,875 times 10 to the power of 13 electrons. It makes sense that it's a big number. Times 10 to the power of 13 is a huge number. It must be big. Now, the rule in physics is you can round off to at least 2 decimal places, which means technically you could say 1,88, but I always tell my students, my calculator gave it to me like that, 3 decimal places. So you may as well leave it like that. So in this case, that is how I use this formula. Remember I said that Q is technically a change in charge? So change is final minus initial. Technically, this 3 microcoulombs is my final charge, and my initial charge is 0. Technically. Because remember, we removed electrons and then gave it that charge, which means initially it had no charge. So imagine an object is no charge, object is a 0 charge initially. That's why it's minus 0. We remove electrons and the final charge is this. But because it's 0, we don't need to include it there. Okay, I'm just showing you that. So if they ask how many electrons were added or removed, or how many electrons are in excess, or how many electrons are in deficit, the Q that you use is basically just the charge of the object. Here's the second scenario in which we use this formula. So when they ask you how many electrons were transferred, or how many electrons are moved from one object to the other, please remember in this case that Q is final minus initial. Now read this question carefully. Sphere A had a charge of 3 nanocoulombs before it was brought into contact with another sphere. So this 3 nanocoulombs is basically its initial charge. Initial means the starting charge, what you started with. Then, after contact with the other sphere, it now has a charge of 1 nanocoulombs. So, after contact, that is the final charge. So basically, we had sphere A and sphere B. I don't know what sphere B's charge is. I don't care. Initially, it was 3 nanocoulombs. Then A and B touched, and something happened over there. And then afterwards, A had a charge of 1 nanocoulomb. B, again, would also be 1 nanocoulomb. Because after they touch, remember, they have the same charge. I don't really care about B in the scenario. They want to know how many electrons were transferred from sphere A. Okay. Now, how does this work? So how many electrons were transferred to or from sphere A? How does this work? Remember, we use our formula. How many electrons? We're looking for N. So you write your formula. Always write your blank formula first. Then Q. Remember, that's final charge minus initial charge. So what was your final charge? Your final charge was 1 nanocoulomb. Remember, that is 1 times 10 to the power of negative 9. Converted to coulombs, nano, 9. Final minus initial. We are minusing the initial charge, which is 3 times 10 to the negative 9. Final minus initial. So you ended up being 1, that's your final, minus what you started with, divided by the charge of an electron. Remember, Whether I put it in as a negative or a positive does not make a difference. But your answer for N cannot be negative. Another very important thing here is the signs are important for this formula as well. So if your initial was a negative, you must put the negative in there. But in this case, my initial was a positive. So that means that this is obviously going to have to be a positive. Just keep in mind that the signs are important. Now, use your calculator. And I get, remember, do not put the negative in. I get 1,25 times 10 to the power of 10 electrons. There we go. And it makes sense once again that it's a big number. Let's take a look at a combination question that you could get asked. We've got A and B. It's clear that these are the initial charges of A and B, but they'll probably say that in the little question that I've just cut out. A and B are now brought into contact and then separated again. And the question wants two things. Calculate the final charge on A after contact and separation, and then calculate the number of electrons that were transferred during this contact. So let's do number one first. How do I know which formula to use? We are told that they contact and they separate. And we want to know the charge after the contact and separation. And they say the final charge on sphere A, but technically they could have said the final charge on sphere B, or the final charge on sphere A and B, because you should know that they will be the same. So what I need to do is, because I'm looking for the final charge after contact, I'm using this formula, Q1 plus Q2 divided by 2. There's two objects, so I'm dividing by 2. This formula is one where I absolutely need to substitute in the signs. I am converting nanocoulombs to coulombs, so times 10 to the power of negative 9. The formula says plus. Then Q2 is a negative. So do you see how I've substituted in the signs? It is extremely, extremely important. Another thing that I often see my students do wrong is they forget to put a plus sign in between these two. The formula says plus. You have to put a plus sign. Then remember the big teacher tip, use your brackets. And I get negative 3 times 10 to the power of negative 9 coulombs. Another way that you could technically write this is negative 3 nanocoulombs, because remember, nanocoulombs just means times 10 to the power of negative 9. What this means is that initially A and B have the charges that you see on the screen, then they touch. Which way will electrons move, by the way? They'll move from B to A, because from more negative to less negative, and then when they separate again, A and B both have the same final charge. They both have the same final charge. My next question, remember, says calculate the number of electrons that were transferred between the spheres. They mean while they were in contact. So what we need to do in order to answer that question is we need to use this formula, because they want a number of electrons. So remember, you write your formula first, always. Okay, it doesn't matter if you say E or QE. Then what we are looking for is N. Remember, Q in this formula is final minus initial. Now you might be like, ma'am, what is the final? What is the initial? We just worked out the final. It was negative 3 times 10 to the negative 9 minus initial. Now you might be like, what? What's the initial, ma'am? The initial is either this charge or it's this charge. And you might be thinking, ma'am, if I can pick which one to use. And yes, you can. You can pick if you want to use this initial or if you want to use this initial. You might be thinking, but ma'am, won't it give me different answers because they're different? It will give you the same answer, because remember, this will be negative 3 minus 2, or it'll be negative 3 minus 8. It'll end up getting you the exact same answer. Just please remember that if you decide to use the negative 8, you must put brackets and you must say negative 8. Let's use that one just to show you. Times 10 to the negative 9. So you're either using that one or your alternative. Let's do both versions here. You can say final, negative 3 times 10 to the negative 9. There's your final. Minus initial. Let's say you choose that one as your initial. I will show you that this gets you the same answer. Remember, E is the charge on an electron. That's a constant. It'll always be 1,6 times 10 to the negative 19. Remember, you can put a negative there, but your answer for n must not be negative. So do both of them on your calculator. Remember to use brackets. Use brackets. It really will make a difference. You get the same answer. Basically what happens is if you calculate just this piece and just this piece, you get the same thing, but one will be a positive and one will be a negative. So this one will be a negative, this one will be a positive. But remember, I don't care about whether they're positives or negatives, because ultimately my answer for n must be a positive. It must be a positive. One or two other things that's super important for grade 10, 11, and 12 electrostatics is that unlike charges attract, there's an electrostatic force of attraction, so they will move towards each other. They attract each other. Unlike charges attract, so opposites attract, they move towards each other. Like charges repel, so they're so similar, they don't like each other, they move away from one another. Electrostatic force of repulsion. Okay. Another thing, the last thing that you need to know is the phenomenon called polarization. So I'll use the first two images to explain. This is a positively charged rod. These balls have a neutral charge. Okay, so they are uncharged. What happens when this rod moves closer and closer, but it does not touch these balls is the following. The electrons in the balls are attracted to this rod. Remember, opposites attract. These things have positive protons and negative electrons in them. Remember, just because they're neutral, remember we said neutral means they have an equal number of protons and electrons. So say they've got 1, 2, 3 protons, 1, 2, 3 electrons. 1, 2, 3 protons, 1, 2, 3 electrons. They are neutral because the number of protons and number of electrons are equal. When we bring the positively charged rod closer, but it's not touching, what happens is opposite charges attract, so all the negatives move to one side of the ball. What that does is that it leaves the one side of the ball more negative. So this side of the ball, this side of the ball has a more negative charge. The other side of the ball, the opposite side, has a more positive charge because it doesn't have a lot of electrons. And that's called polarization because the balls develop a negatively charged pole and a positively charged pole. And that's it for the theory that you need to know. Please let me know if you'd like to see more, past paper questions such as these ones, in more detail in videos to come in the future. I'm so happy to do it. Please check out my playlist for more electrostatic videos, and I can't wait to see you guys in another video very, very soon. Goodbye, everybody.